Good morning, dear students. Myself Sachin S. Pawar, and I welcome you to my 8th video on Unit 1 Solid States for PU2 Chemistry students. In my last video, we have covered defects in solids, in particular stoichiometric defects. In today's class, we shall go for non-stoichiometric defects. So let's begin our today's session. Non-stoichiometric defect. Now when I say non-stoichiometric defect, you must understand non-stoichiometric defect means the stoichiometry which is there in the solids, that is the ratio of the atoms, ratio of the ions get disturbed, and that is the cause to show that it is a non-stoichiometric defect. Non-stoichiometric defect means the ratio of the ions will disturb. We shall understand this with examples and many other things in this particular slide. So let's begin our today's session. Non-stoichiometric defects. Okay. So non-stoichiometric defects. Non-stoichiometric defects are mainly of two types. We have mainly two types of defects, non-stoichiometric defects. One is called as metal excess defect. One is called metal excess defect, and second one is called as metal deficiency defect. Metal excess defect and metal deficiency defect. So non-stoichiometric defect. When I say metal excess defect, remember these are the defects occurring in the ionic solids, and ionic solids have got cations and anions. So when I say metal excess defect, it means the number of cations are more, and when I say metal deficiency defect, means number of anions are more and or number of cations are less. So let's go for that. Metal excess defect. Okay. So metal excess defect means a point defect in which it is a non-stoichiometric defect. It is a non-stoichiometric defect. It is a non-stoichiometric defect. Okay, and it arises due to excess of cations present in the system. It is due to presence of extra cations in the system. Whereas metal deficiency means it is also a non-stoichiometric defect and it is a point defect. But here you see there is a deficiency in the positive ions. That means number of anions are more in number. Number of anions are more in number. Okay. So let's see some examples on this. Okay. Non-stoichiometric defect. As I told you, non-stoichiometric crystal is the one. So here, because of this defect, the crystal becomes non-stoichiometric, or the compound becomes non-stoichiometric. That means what? That means the ratio of the positive and negative ions, the ratio of the positive and negative ions are disturbed, are differed from the ideal composition. Like for example, if I take sodium chloride, the ideal sodium chloride, if I just take an example, say sodium chloride, the ideal sodium chloride is NaCl. The ratio is 1:1. Ratio is 1:1. So here, if it has this non-stoichiometric defect, then the ratio will be disturbed, and this is ideal, and it will differ from this. Then it is called non-stoichiometric defect. Okay, and the compound is called non-stoichiometric crystal or a non-stoichiometric compound. One example I will give you in a later stage. Metal excess defect. Let's move on to the first one, that is metal excess defect. So when I say metal excess defect, it can happen in two ways. When I say metal excess defect, we are talking about cations and anions. If cations are less, then the number of anions will be more. So in that case, it becomes number of cations will be more. If number of cations are less, then anions will be more. And if the number of anions are more, then cations will be less. So here metal excess defect is of two kinds. One is anion vacancies, metal excess defect due to anion vacancies, and metal excess defect due to presence of extra cations at the interstitial site. The two possibilities: metal excess defect due to anion vacancies or a metal excess defect due to presence of extra cations at the interstitial site. Let's see the example here. I have one crystal here. A crystal is which I have taken is crystal AB. Here it has got A plus and B minus ions. This is a cation and this is an anion. Okay, so if you just see here, anion vacancy means, just see in this particular structure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cations are there. 1, 2, 3, 4, 5, 6, 7, 8, 9 anions are there. Means some anion vacancies are there. So here you see this red color circle. Here the anion is missing. Anion is missing from their lattice point and it is occupied by an electron. So this is anion vacancy. Anion vacancy. It is an anion vacancy. It is an anion vacancy. Anion vacancy. And in the presence of extra cation, if you just check the presence of extra cation, then you see here what you have is one extra cation is occupying the interstitial space. An extra cation is occupying the interstitial space. So the ratio here it should be 1:1 ratio, but here you see the number of anions are disturbed, so number of B minus ions are less, and here you see number of A plus ions are increased, and this is a metal excess defect in terms of anion vacancies and in terms of presence of extra cation. Now one important thing to be understood here is, like for example here anion vacancy means some anions are missing. Some anions are missing. So when the anion misses, the amount of negative charge decrease, and the amount of positive charge increase. But in ionic solids, electrical neutrality need to be maintained. That is the total positive charge should be made equal to total negative charge. For this purpose, what happens is, when the anion leaves its lattice site, that is the point where there is a pink color spot, when the anion is leaving the site, when it is leaving, it will leave its electron at that place. And this when the electron is left here, this space is referred to as anion vacancy, and it is referred to as F center. Here also you just check presence of extra cation. When an extra cation is occupied, when an extra cation is coming, so here from external source a cation is coming. So here the amount of positive charge has increased and the amount of negative charge has decreased. To counterbalance the charges, positive ion is increased means some extra electrons will go and occupy some other interstitial site. So here we have extra electrons. At the interstitial site. So this is metal excess defect in terms of anion vacancies and in terms of presence of extra cation at the interstitial site. Because of this, you see one simple thing what happens here. In anion vacancies, when the anion leaves the site, it gives electron here. It gives an electron here in the lattice site. So this is anion vacancies so this is anion vacancy and presence of extra cation at the interstitial site leading to metal excess defect. So these are the words. A compound may have extra cation if the negative ion is absent from the lattice site. So here some negative ions are missing from the lattice point. Because of that, some empty sites, the empty sites are occupied by electrons, that also I have told you. Here some cations, an equal number of electrons to nullify the charge difference occupy at the interstitial site. This is the anion vacancies and presence of extra cation at the interstitial site. Okay. Anion vacancies, when I say, so here this is the anion vacancy site. This anion vacancy site has lost an anion. So B minus ion has been removed from here. B minus ion has been removed from here. So when this B minus ion is removed, it gives its electron here, and the electron of this B minus ion comes and occupies here, and this site is known as F center. F center is actually a center where the electron is trapped. The electron is trapped in the anion vacancies, and that is referred to as F center. The word F center is a word obtained from a German. It is a German word. F center is a German word which is meaning is color. Actually what happens is, because of this electron in the anion vacancy site, compound will have a certain color. What is that, how it is, that we shall see in the next slide. Okay, so consequences of metal excess defect. So I just told, metal excess defect, it can be due to anion vacancies. In anion vacancies, some anions leave the lattice sites, electrons come there, those places become F centers. In metal excess defect, some extra cations along with some extra electrons go to the interstitial site. Because of this, what will happen? The consequences of metal excess defect. The first effect. See, both have given us electrons in their in the anion vacancies. The electrons come in the F centers, and in metal excess defect also we have electrons in the interstitial site. That means we have free electrons. Available, and these free electrons can carry current as we pass electricity, and therefore metal excess defect makes the crystal to start conducting electricity. Because of metal excess defect, the crystal starts conducting electricity because the free ions are available, and these free electrons starts conducting electricity. So here now free electrons are conducting electricity, and as you have learned from physics, when the electrons are conducting, here it is going to be a n-type semiconductor. It will become an n-type semiconductor. So it will become an n-type semiconductor. That means the electrons are responsible for carrying the current. The details about this n-type semiconductors we shall see in the last part of this topic. Okay, so this is the consequence number 2. Consequence number 3 is, there are free electrons, and these electrons are unpaired. We have unpaired electrons. See, we have unpaired electrons, we have free electrons, we have unpaired electrons at this site. At this F center, we have got unpaired electrons. These unpaired electrons, and you have learnt in PUC first year chemical bonding that if you have unpaired electrons, because of their spin motion, they will have magnetic character and they become paramagnetic. Detail about these also we shall see in the last part of the topic. Okay. So these are the consequences of metal excess defect. One more last consequence is why it is called as F center. That you will understand. So here the crystal, when there is a metal excess defect and the electrons occupy the F centers, in the anion vacancies, the crystal starts giving out or appearing some different colors. Like for example, sodium chloride, potassium chloride, lithium chloride, they are actually colorless solids. They are all colorless solids. But in presence of excess of sodium chloride becomes yellow in color. Potassium chloride, in excess of potassium, it gives you a violet color or a lilac color. And excess of lithium in lithium chloride gives us pink color. Why it happens? With this, why it happens, that we shall see in this particular example. I'll take the first example and I'll explain you why it happens, and then we'll go further into the next part. Okay, so I'll take the first example here. In excess of sodium chloride, even though it is white in color, it appears yellow. Why? Let's see this. So when a sodium chloride is heated in an atmosphere of sodium vapor, it acquires yellow color. Why? Now think of this on the basis of metal excess defect due to anion vacancies. So what happens here? First part, sodium chloride is heated in an atmosphere of sodium. So sodium vapors are taken. We have a sodium chloride in a crucible or in a container, and we are passing sodium vapors onto it, and we are heating it. When you heat it, what happens is, on the surface of sodium, the first thing what happens is, suppose I have a surface, so I have a sodium chloride crystal. This is sodium chloride crystal. So on the surface of sodium chloride, some sodium atoms get deposited. So from the vapors, sodium vapors we have, these sodium vapors get deposited on the surface. They get deposited on the surface of the crystal. And some anions, some Cl minus ions which are there, those Cl minus ions leave the site. They diffuse out of the surface. Because of this, what happens? Let's see. Because of this, chloride ions on the surface of NaCl crystal. So on the surface we have sodium atoms. Those chloride ions, when they are coming out in the crystal, so those chloride ions which are there, the chloride ions on the surface, and we have sodium atoms already on the surface, they will react and they will form sodium chloride. Just see what happens here is, an electron has to be ejected out of it. So one electron is ejected. This electron which is ejected will enter into the solid, and it will go to the lattice site of an ion from where that has come, and we call that as F center. And this electron will rest there. It will not rest there, it will start oscillating there, and because of oscillation of electron at that F center, there will be excitation and relaxation of electrons. Excitation will absorb energy, and absorbed energy will be released out again when that excited electron jumps back to the normal state. So during that process, electrons vibration, some energy is emitted, and that energy is emitted which corresponds to yellow color, and therefore in the vapors of sodium chloride, when you heat sodium chloride becomes yellow in color. So this is the example. Okay, so these electrons absorb energy in the F centers. The electrons absorb energy, they got excited, and they starts vibrating emits energy, and that energy is emitted which corresponds to yellow color, and therefore we have yellow color sodium chloride in the atmosphere of sodium vapors in the heating position. Okay, let's move ahead into the next part. Zinc oxide. If you just take second example, a zinc oxide is heated it acquires a yellow color. When you heat zinc oxide alone, it acquires yellow color. Why? Here, explanation. Zinc oxide is primarily a white color substance at room temperature. When you heat it, the reaction takes place. The reaction is, zinc oxide will decompose into Zn plus 2 ions, oxygen and 2 electrons. So here Zn plus 2 ions and 2 electrons are formed. So zinc oxide is a white colored substance at room temperature, but it turns yellow on heating due to loss of electrons. So electrons are lost. Those electrons which are there, those excess of zinc plus ions occupy the interstitial site, and these electrons, see what happens here is, these zinc plus 2 ions and 2 electrons which are ejected, both will go to the interstitial site. And when they go to the interstitial site, electrons are there, they'll start vibrating, and electrons will be responsible for again the color to impart, because electron starts vibrating, and because of the vibration of electrons, the energy is emitted, and that energy corresponds to yellow color. So here you see, in case of sodium chloride, color is imparted due to anion vacancy, And in zinc oxide, the color is imparted due to occupancy of zinc plus 2 ions and electrons into the interstitial site. So one example each I have just covered for that purpose. Okay, let's go into the next. Metal deficiency defect. So I have just covered metal excess defect. Excess of metal can take place either by anion vacancies or by presence of extra cation at the interstitial site. So in a reverse way, when I go for metal deficiency defect, number of cation should be less, and that is possible by two ways. Absence of metal ions from the lattice site, that is the requirement. Here the metal ions are less in number. And that can happen in only two ways. One way is that there can be a cation vacancies. That means some cations leave their lattice site and give the empty space. Or another possibility is that some extra anion may go and sit in the interstitial site. Two possibilities are there. So metal deficiency defect can take place in two ways. The ratio of the cation and anion should be changed, and we are required here metal deficiency, means cation should decrease. Means either we remove cations from their lattice sites, so we have cation vacancies, or you add an extra anion, to the interstitial site. Two possibilities. Let's see the examples for this. Here, cation vacancies. So just see the diagram here. If you just see metal deficiency defect due to cation vacancies, if you see it here, what happens is here a cation is missing from their lattice site. This site, if you just take, a cation is missing from their lattice site and is creating a cation vacancies. Okay, and here in this particular case, if you just take, some anion is occupying the interstitial site. Okay, now electrical neutrality need to be maintained. That is a requirement. That is, the total number of positive charge should be made equal to total number of negative charge. Now in this diagram, if you just take, one B minus ion has been removed from the lattice. So one negative charge has decreased. One negative charge has been removed. So to maintain that neutrality, one positive charge need to be added. So what happens here, if you just concentrate on a neighboring cation, which was A plus, will become A plus 2, so that the charges get balanced. One negative charge goes, one positive charge comes, means we have equal neutrality. Neutrality is maintained. So here, when a cation is missing from this lattice site, the neighboring cation will acquire higher oxidation state, will acquire higher positive charge, so that electrical neutrality is maintained when we have a cation vacancy defect. In case of metal deficiency defect due to extra anion, when an extra anion is present, so extra anion is present means there is one extra negative charge. A negative charge has increased. So to compensate that, neighboring cations, to make the neutrality, that is positive and negative charge equal, some neighboring anions, you see here, they acquire some higher positive charge, so that the number of positive charge become equal to number of negative charge, and that is one of the requirement for metal deficiency defect to take place. So metal deficiency defect, when I say, in a cation vacancies, cations leave their lattice site. Cation vacancies means cations are leaving the lattice site, and when the cations are leaving the lattice site, number of anions will increase, and the cations are removed, means the positive charge is decreased, and to increase that positive charge, some neighboring cations will have higher positive charge, so that balancing is there. In presence of extra anion, what happens? You are adding an extra negative charge. So to compensate that, the neighboring cations will acquire a more positive charge, so that the charges are compensated. This is about the metal excess defect and metal deficiency defect in case of cation vacancy and presence of extra cation at the presence of extra anion at the interstitial site. Okay. Presence of extra anion at the interstitial site. Now I said presence of extra anion at the interstitial site. Now you know one important thing is that if I take anion, say B minus ion, then size, you know one thing, that if I take an atom in terms of size, if I say, then size of the atom is greater than the size of the cation, because here the electrons are removed, and size of the anion is greater than the size of the atom, because here the electrons are added. That I have already told you in the last class also, and you have learnt it in periodic table also. So here size of the anion size which is there is large, and since the size of the anion is large, the interstitial space which is available, that space is very small compared to this large size, and therefore occupying this large size into this small interstitial space is a very difficult task. A small space cannot occupy a large body, and that's why a metal deficiency defect which is involving presence of extra anion at the interstitial site is very uncommon. It's not commonly observed. It is not commonly observed because of the greater size or the larger size of the anion, which makes it unfit to go into the interstitial site, which is smaller in size in comparison with it. Okay, so let's go ahead into the next, cation vacancies. I have just given explanation. Let's see one example. Ferrous oxide is one example. Which is giving you a cation vacancies. So here the ferrous oxide, if I just take, then the ratio of the ferrous oxide ion is Fe+2. We require Fe ferrous oxide formula we usually write. Ferrous oxide, we usually write it as Fe+2 and O-2. So the ratio is 1:1. The positive charge and a negative charge is 1:1. So here, but the problem here, so the empirical formula which we write it as FeO, but in actual practice it is not that. The formula of ferrous oxide is Fe.95, and it ranges between 0.93 to 0.96. Why? It is because of cation vacancies. Let's see what happens. Because of cation vacancies. It happens because of cation vacancies. Let's see the detail about this. Here we have a cation vacancies. Means what? Some Fe+2 ions are missing from their lattice site. Some Fe+2 ions will miss from their lattice site. So cation vacancies need to be created. In ferrous oxide, some cations leave their lattice site. So when they leave their lattice site, what happens? Positive charge has decreased. The positive charge is decreased. Okay. So when the positive charge is decreased, what will happen? The neighboring cations will have to have a greater oxidation state. So neighboring cation will have a greater oxidation state. So Fe+2. So I'll just show this by a diagram. Okay. Suppose we have Fe+2, O-2, Fe+2, O-2, Fe+2, O-2, Fe+2, O-2, Fe+2. So here we have this. Suppose one Fe+2 ion is leaving the site. So suppose this Fe+2 is going out. So here you see a positive charge is disturbed. So here when Fe+2, so this is a cation vacancies. It is a cation vacancy. So it is Fe+2 cation vacancy is created. Because of this, the charges, you see the charges are unbalanced. Here see minus 2, minus 2, minus 2, minus 2, that is minus 8. So minus 8 charge, total negative charge is minus 8, plus 2, plus 2, plus 2, plus 2, that is, sorry, I have to take a few more. So here the charges are nullified. I'll just take few more. Better I'll take O minus 2, Fe plus 2, O minus 2, and so on. So here one cation vacancy is created. So here Fe plus 2 is gone. One Fe plus 2 is gone. That means the ratio of the positive and negative ion is disturbed. So to compensate that, the neighboring, what happens is the neighboring, one of the neighboring anion, cation will acquire, will lose one electron, and becomes Fe plus 3. Will become Fe plus 3. So this becomes Fe plus 3. So this becomes Fe plus 3. One Fe plus 2 goes, and Fe plus 2, one Fe plus 2 becomes one Fe plus 3. And that is the reason for that is, because of that what happens is the ratio of Fe plus 2 ion, the ratio of Fe plus 2 and O minus 2 ion, which should be 1:1, is disturbed, because some Fe plus 2 ions are missing, so the ratio is disturbed, and we have a cation vacancy. And this completes the metal excess defect and metal deficiency defect of solids. The detailed idea of this. Okay, so consequences of metal deficiency defect we shall take, and we'll go for that. Okay, so in metal deficiency defect, cations are going out. The number of cations are less. So what happens? Cations are less means holes are created. Cation vacancies are created. Cation holes are created. So cations holes are created. Cation holes are created, and electrons are not here. It is a empty space. So cation holes are created. So presence of extra hole, that hole is responsible for conducting electricity. So electricity, the conducting capacity, the electricity conducting capacity of the metal increases because of the holes. Because what happens when you pass electricity or energy to this, what happens is, suppose this A plus will absorb energy, and it starts vibrating, and when it is vibrating, it will shift its position from here to here. As a result, this B minus will shift from here to here, and the process of shifting, the energy absorbed by that ion is passed on from one place to other place, and that is why the conductivity is there, and the conductivity is due to the presence of holes. So movement of holes is responsible. The movement of holes is responsible for conduction of electricity. That is why it should be a p-type semiconductor. It should be a p-type semiconductor. So metal deficiency defect leads to p-type semiconductor, whereas metal excess defect leads to n-type semiconductors. This is all the today's class. Non-stoichiometric defect, two types: metal excess defect, metal deficiency defect, and examples each for this. Example for the last class of compound is not there in your syllabus. Why? Because the size of the anion is very large, and it is very difficult to have that large anion into a small interstitial space. So example for this last part, that is a metal deficiency defect due to presence of extra anion at the interstitial site, is not mentioned. Okay, this is all for today's class. The remaining part we shall see in the next class. Thank you. I'll stop here.